All right, let's jump straight into this explainer. If you're gearing up for your FCS intermediate exams, you already know the body's metabolic and inflammatory response to trauma is an absolutely massive topic. I mean, it's incredibly dense. But it's also one of the most heavily tested areas you're going to face. So what we're doing right now is transforming this complex physiological cascade into a high-yield, structured, and totally memorable summary.
To make this stick, we're breaking it down into 6 critical areas: the ebb and flow phases, the inflammatory immune response, the second hit phenomenon, hypercatabolism and metabolic alterations, mitochondrial dysfunction and energy, and finally, the liver's critical role.
Starting us off with Section 1, the ebb and flow phases, the survival timeline.
Now, this timeline right here is literally your foundational scaffold for understanding trauma physiology. First mapped out by Cuthbertson back in the 1930s, the initial injury kicks off an immediate ebb phase. This lasts less than 24 hours, and honestly, it is all about pure, immediate survival. If the patient makes it through that, they hit this explosive flow phase, where the catabolic process typically peaks around day 2 or 3. Finally, if that initial insult resolves, usually within 5 to 10 days, the body shifts into an anabolic state to start rebuilding.
Examiners absolutely love testing the stark contrast between these first two phases. You really need to picture the hypometabolic shutdown of the ebb phase. Decreased cardiac output, lowered basal metabolic rate, blood shunting to vital organs, and contrast that against the hypermetabolic fireworks of the flow phase. That flow phase is all about massive neuroendocrine flux. We're talking huge surges in catecholamines and cortisol, driving explosive immune activity and rapid protein breakdown.
Moving right along to Section 2, the inflammatory immune response, the first responders. So, how does the body actually know it's been injured? Well, it all starts with the innate immune system, and for your exams, you have got to trace this exact cellular pathway. The body recognizes pathogen-associated molecular patterns, or PAMPs, like lipopolysaccharides from gram-negative bacteria. These latch on to toll-like receptors, specifically TLR4 binds LPS. The big takeaway here is that this binding unleashes the NF-kappa B signaling pathway. NF-kappa B moves to the nucleus and acts like a master switch, cranking out a massive wave of pro-inflammatory cytokines.
But wait, what if there's no bacteria? Say it's a sterile surgical trauma or a blunt force crush injury. Well, that is exactly where alarmins, also known as damage-associated molecular patterns or DAMPs, step up. Molecules like HMGB1 or heat shock proteins get released by dying tissue, and they act exactly like those bacterial PAMPs to sound the alarm and trigger the exact same inflammatory cascade.
And these triggers perfectly illustrate how the resulting pro-inflammatory cytokines, especially tumor necrosis factor or TNF and interleukin-1, get to work. These guys are your early-acting heavy hitters. They work together synergistically to amplify the whole immune response. They reset the hypothalamus to cause a fever, they massively activate immune cells, and they crank up endothelial permeability. That permeability, by the way, is exactly what causes that classic post-op fluid leak and edema.
Next up, Section 3, the second hit phenomenon, clinical complications.
I want you to really think about this scenario because you'll see it all the time in the ICU. If a patient is already deep in that hypermetabolic flow phase from their first trauma, how on earth does their immune system handle being rushed back into the OR for a complication or getting hit with a brand new post-op infection?
Well, the answer lies in the two-hit model. The body's reaction to a second insult is totally unpredictable. You've got a depleted, confused immune system that develops innate immune tolerance and a seriously diminished capacity to fight the new threat. But at the exact same time, there's this persistent, dysregulated, systemic pro-inflammatory activity going on. This lethal combo can rapidly spiral into systemic inflammatory response syndrome, or SARS, and ultimately multiple organ failure.
All right, Section 4, hypercatabolism and metabolic alterations, fueling the war effort.
Here, we're shifting from inflammation to metabolism, because the body literally breaks itself down to fuel this massive war effort. This hypercatabolic syndrome creates a huge metabolic shift. The patient isn't eating, and liver glycogen is gone in about 24 hours, so the body has to make its own glucose. Amino acids get stripped from skeletal muscle, glycerol gets mobilized from fat, and it's all forcefully pushed to the liver. The liver then uses these to pump out glucose via gluconeogenesis just to keep the brain and vital organs running.
And to understand this muscle wasting on a molecular level, which is super high yield for the boards, you've got to remember this specific interaction. Skeletal muscle breakdown is driven hard by cytokines, but look closely at the pathways. TNF's effect on muscle breakdown is primarily driven by glucocorticoids. On the flip side, IL-1 causes proteolysis through a totally independent pathway.
Diving into Section 5, mitochondrial dysfunction and energy. The engine fails.
You need to memorize this exact sequence of mitochondrial doom. Trauma, especially with hemorrhage, causes ischemia and hypoxia. Without oxygen, cells are forced into inefficient anaerobic glycolysis. This rapidly drains ATP and sends lactic acid levels spiking. The end result of this energy crisis? Mitochondrial swelling, transition pores opening, and the triggering of apoptosis, or programmed cell death.
Because without adequate blood flow delivering fuels and oxygen, the mitochondrion fundamentally breaks down. It flips from being a life-saving energy producer into a toxic generator of reactive oxygen species, or ROS. And that causes massive, often irreparable oxidative damage to cellular DNA and membranes, making organ failure even worse.
Finally, Section 6, the liver's critical role, the central metabolic coordinator.
Let's look at the hardest working organ during the trauma cascade. For the exams, you must differentiate the specific jobs inside the liver. Contrast the immune clearance role of the Kupffer cells, those are the resident macrophages clearing endotoxins and pumping out IL-1 and IL-6, against the heavy metabolic lifting of the hepatocytes. The hepatocytes are the actual factories, shifting gears to support gluconeogenesis, clearing nitrogen waste through ureogenesis, and manufacturing essential proteins.
Speaking of proteins, those hepatocytes furiously manufacture acute phase proteins in response to those Kupffer cell cytokines. A massive high-yield point here is C-reactive protein, or CRP. It actually binds to phosphocholine on dying cells in bacteria, tagging them so macrophages can eat them, but paradoxically, while all these acute phase proteins are being churned out, circulating albumin levels drop. Albumin acts as a negative acute phase protein, mostly because that massive capillary leak we talked about earlier is pushing it out into the extravascular space.
And because of this massive shift in protein synthesis, the liver drastically cranks up procoagulant factors like fibrinogen and factor VIII, while dropping anticoagulant factors like protein C and antithrombin 3. Because of this, the trauma patient enters a highly dangerous hypercoagulable state. This physiological reality right here is exactly why DVT prophylaxis is practically a religion in surgical recovery.
So I'm going to leave you with this final thought as you push forward with your FCS intermediate prep. The inflammatory and metabolic stress response is perfectly designed by evolution to save the patient from an immediate threat. But in a modern ICU, at what point does our surgical and medical intervention become the tool we need to save the patient from their own overzealous response? Truly understanding that balance is what's going to make you not just a great exam candidate, but a phenomenal surgeon. Thanks for tuning into this explainer, and happy studying.